Okay, so our last talk for today is from Sebastia Reyes Carocca from Universidad de la Frontera. And he will give a talk about Abelian varieties and Riemann surfaces with generalized quaternion group actions. Thank you, Sebastian.
Thank you very much, Paola. Thank you very much, everyone. Okay, this is a joint work with Ángel Carocca and Ruby Rodriguez. And let me start by introducing the basic objects. A compact Riemann surface or a Riemann surface, we always, we will consider in this talk always compact Riemann surface. This is a complex analytic manifold of dimension 1, and we can consider the moduli space of these objects, MG, the moduli space. It has a structure of complex analytic space. It is well known that the dimension is 3G minus 3. And it has singularities, and if the genus is at least 4, the singular locus of the moduli space agree with the points representing compact Riemann surfaces with non-trivial automorphisms. So to talk about Riemann surfaces with automorphism or with group action means to work with the singular locus of the moduli space. And there is very classical results. Of course, the automorphisms form a group structure. They have group structures, and if the genus of the surface is at least 2, this group is a finite group, and the order is bounded by 84 times G minus 1. And on the other hand, each finite abstract group can be realized as a group of automorphisms of a compact Riemann surface of a suitable genus. And there is several ways to study Riemann surfaces, of course, as an analytic object, according to our definition. There is an equivalence with algebraic curves. And also we can study Riemann surfaces as quotients of the action of Fuchsian groups on the upper half plane. So Fuchsian groups are just discrete subgroups of the automorphism group of H. So there are several point of view to study Riemann surfaces. And let me spend some words about Fuchsian group. We always assume that the Fuchsian groups are compact, the quotient is compact, and we can talk about the signature of the Fuchsian group. This is a tuple of numbers where the first number H is the genus of the quotient, and the numbers M1 to ML are the branch indices in the universal canonical projection. And triangle Fuchsian groups are those with this signature, genus 0 downstairs and only 3 branch bars. Okay, Riemann existence theorem provides necessary and sufficient conditions in order to a group act on a compact Riemann surface with a given signature. If we have the Riemann surface written as a quotient as if we write the Riemann surface H divided by the action of Fuchsian group gamma, an abstract group G acts on the Riemann surface if and only if there is epimorphism theta from the Fuchsian group delta to the abstract group G in such a way that the kernel of this epimorphism agree with the Fuchsian group gamma, which uniformize the Riemann surface. And we said that the group G acts on the Riemann surface with the signature of the Fuchsian group delta. And also there is a relation between the numbers involved here as the genus of the surface, the genus of the quotient, the numbers, the branch indices, and the order of the group, which is the degree of the associated map given by the action of the group G. Okay, let me show you an explicit example, very explicit. For example, we can fix this signature and consider a Fuchsian group delta with this signature. There is a canonical presentation of this group written in yellow. And we can consider this group. This is a group of order 20, this outer group, and we construct the map theta written in terms of the generators gamma 1 to gamma 4. If we send these elements to these elements of the group, we have a surjective as an epimorphism as in the previous theorem. So the quotient of the upper half plane by the kernel of this map is a compact Riemann surface, and the abstract group G by 4 acts on this Riemann surface with the starting signature. This is the idea how we can construct group action Riemann surfaces, and in order to compute the genus of the Riemann surface, we apply the Riemann-Hurwitz formula. In this case, the genus of the surface is 6. So as a conclusion, there exists a compact Riemann surface of genus 6, admitting the action of this group with this signature. And we have a picture like this part. Upstairs, we have the Riemann surface, and those downstairs, we have the Riemann sphere or the predicted line with 4 branch values marked with 2, 2, or 4. Moreover, we can normalize the branch values, and there is only one free parameter, complex parameter free. So indeed, we have a family of Riemann surfaces with this property. So inside the singular locus of the modular space of Riemann surfaces in genus 6, we have a one-dimensional family, complex one-dimensional family, and all the members of this family admit the action of the same group with the same signature. This is it. Okay, this is compact Riemann surfaces. Let me talk about Abelian varieties. And Abelian variety is just a complex torus, which is also projected. And this is equivalent to say that the complex torus admits polarization. And as in the case of Riemann surfaces, we denote by AG the modular space of principally polarized Abelian varieties. It has also a structure of complex empty space. The dimension is well known. And as in the case of Riemann surfaces, the singular locus agree with those points representing Abelian variety with non-trivial automorphism. And non-trivial means different from the identity and minus the identity. Okay, and the relation between these objects is the Jacobian variety. If we have a Riemann surface S of genus G, we can consider the vector space of one forms and the first integral homology group. And we can construct this quotient, the dual of this vector space, divided by the action of the homology group. And we obtain what we call the Jacobian variety of S. And this is an Abelian variety. Principally polarized Abelian variety. The dimension of the Abelian variety is the genus of the Riemann surface, and this Abelian variety is also irreducible. And we have this very famous theorem that said that this map, the map which takes Riemann surface and send it to its Jacobian, is injected. So two Riemann surfaces are isomorphic if and only if the respective Jacobians are isomorphic as principally polarized Abelian varieties. Okay, as in the case of Riemann surfaces, the automorphism groups of polarized Abelian variety are finite. Each finite group can be realized as a group of automorphism of an Abelian variety. And let me give you an explicit example. For example, we can consider these matrices R and S. We construct these matrices R and S, capital R and capital S. And it's easy to verify that R and S belong to the symplectic group, and they generate a group isomorphic to the diagonal group of order 20. So we have a realization of this abstract group in terms of symplectic matrices. Now we can define this set, the set C Gothic 5, the matrices in the Siegel upper space of this form. Here, U, B, and W are complex numbers, and of course, under the restriction that they belong to H5. And we can verify that the matrices of this form are invariant under the action of the group generated by R and S. So we can consider now we have the canonical projection from H1, C1 is inside H5, so we can consider the projection under P, and what we obtain a family of abelian varieties. Each matrix, as before, give rise to an abelian variety. This is the idea. So we have three parameters, this is a three-dimensional family of abelian varieties of dimension 5, all of them of the same dimension, and all the members admit the action of the diagonal group. And in some sense, that I'm going to explain later, all the members share the same action, the same analytic representation of the group. And it is possible also to prove that the family contains a family of Jacobians. Yeah? So this is the relation between abelian varieties and Riemann surfaces with the group action. So let me go to the general problem. The general problem is the following. If we fix a class of groups, we want to study compact Riemann surfaces and abelian varieties admitting an action of a group in this class. So we fix the class of groups and we study abelian variety and Riemann surface admitting a group in this class. This is a very general problem, so we can consider ideas and sub-problems, for example, to restrict the previous general problem to some special situations, consider the case of families and rigid points, classify different actions of the same abstract group, study intermediate covers, determine isogeny decomposition. There are several aspects we can consider from this general problem. And today I want to talk about what happened if we fix the class of groups, which are called the generalized quaternion groups. These are group of order 2n, and this is the presentation. It's presented in terms of two generators and with this structure. This is not a semi-direct product. Okay, so the idea is to study compact Riemann surfaces and abelian variety with a group of automorphisms isomorphic to this yellow group. Okay, let me start with the isogeny decompositions. This is very general theory. If we have an abelian variety and we have a group of automorphism, there is an induced Q algebra homomorphism from the rational group algebra to the rational endomorphism algebra of the abelian variety. And once we fix an element in the left part, by considering the image of the image, we obtain an abelian subvariety of A. This n is just, it doesn't matter the role of n in this case. So we consider an element E, we consider the image here, and then the image, and we obtain an abelian variety. And the idea behind the theory is that we can decompose the one in terms of sum of appropriated idempotents in Q G. And we can translate this way to write the number 1 to the right part and in order to obtain an isogeny decomposition of the abelian variety in terms of abelian subvarieties of the original abelian variety, which are pairwise non-G isogenies. There is no anisogeny between two factors with respect to the action of the group. This is the idea. Moreover, each one of these factors can be decomposed further, and we obtain a decomposition in this way in terms of several factors or components factors with some multiplicities. And both the factors A and B's depends on the group structure, or more precisely depends on the representations of the group. And this is a very important remark. The group algebra decomposition does not depend on the way the group acts. So it only depends on the algebraic structure of the group. And let me introduce important abelian subvarieties. One we have for each subgroup of the group G, we can consider this element of QG. This is the E of the previous part. and we can consider the Abelian subvariety associated to this element, and we denote this A sub k. Of course, k, by construction, acts trivially on this Abelian subvariety. And this is the idea, and the idea is to emulate the role of the Jacobian of the quotient. If we have a Riemann surface S, we have the Jacobian. So this is in particular an Abelian variety. So if A is a Jacobian, the canonical subvariety on which K acts trivially, in this case, is isogeny, isogenous to the Jacobian of the quotient of S by K. And more generally, if we have two subgroups of this form, we have AK2 and AK1, they are related in this way, and there is an Abelian subvariety of A in order to obtain an isogeny, like in the green equation. And this P, we denote this P with this symbol because we are, this is the analog of the prim of a cover between two, associated to a cover between two Riemann surfaces. Okay, so we need the subgroup of the group G. Remember that G is the quaternion group, the generalized quaternion group of order 2n. So we have in green the subgroups of G, and we are going to give the an isogeny decomposition in terms of this subgroup. And we, in red, we have written some subgroups with a different letter because they have a very special role, but they are the yellow subgroups are contained in the green subgroups. Yep. So the idea is to decompose the Abelian variety in terms of factors where each factor has a geometric meaning. And this is what we did when we have an Abelian variety A with a group of automorphism G isomorphic to the generalized quaternion group. We have an isogeny decomposition like this in terms of several factors. Each one of them has a geometric meaning. So this is the canonical subvariety fixed by G. This is the prim variety associated to these subgroups and so on. Moreover, we can go further, and the group algebra and two group algebra decomposition of A are given by this isogeny and this isogeny. So as a conclusion, we can decompose an Abelian variety with the reduction of this group in terms of several factors. Each one of them has a geometric meaning in terms of prim varieties or canonical subvarieties. And the ideas behind the proof is a carefully study of the rational and complex irreducible representation of the group. We need to consider induced decomposition. When we have a decomposition of A, we have an induced decomposition of AK, so we have to study that, and also to study induced decomposition by subgroups of J. And this interesting fact that each factor has a geometric meaning, in general, is not true. So we were lucky. And also, it can be deduced from the proof of the theorem that there are isogenies between these prim varieties, which are also interesting. Okay, let me recall again that the group algebra decomposition only depends on the way, only depends on the group structure of G, and it doesn't depend on the way the group act. For example, this is an example. In the case of Jacobian, the group of order, the cyclic group of order 2 acts on genus 2 in two different ways. These are the pictures. And the group algebra decomposition in the first case does not provide any information. But in the second case, the Jacobian variety decomposes in terms of two elliptic curves. So here, the group algebra decomposition also is something like E1 times E2, but the dimension of E1 is 0. So the dimension of E2 must to be 2, and there is now a decomposition. Yeah. This is the idea. The group algebra decomposition is the same, but the dimension of the factors depend on the way the group acts. So the dimension of the factors is encoded in the analytic representation of the group. So in the case of Abelian variety, in the case of Riemann surfaces, we can be more precise and to say that the dimension is encoded in the signature or in the epimorphism theta of the first part of the top. So the analytic representation of the group, of course, can be written in terms of as a direct sum of the irreducible, complex, irreducible representation of the group. So we need to fix notation, and the complex, irreducible representation of the generalized quaternion group are denoted by T1, 4, and 3 and 4, and theta, capital theta S. We have several complex irreducible representations. This is the full set of pairwise non-equivalent complex irreducible representations. So the analytic representation, which is in general is not irreducible in general, can be written in terms as a sum of the irreducible component, irreducible representations, and the dimension of the factors appearing in the group algebra decomposition can be written in terms of these numbers, the multiplicities of the complex irreducible representations. And it's very clear or very easy to, if we know explicitly the analytic representation, we can compute explicitly and in an easy way the dimension of the corresponding factors. And this is the idea. Okay. Of course, the dimension, as we saw in a previous example, the dimension of a factor in the group algebra decomposition can be 0. And in an extreme situation, all the factors are 0-dimensional with the exception of only one. In this case, of course, we don't have a decomposition. And in this case, we said that the group algebra decomposition is trivial. All the factors are 0-dimensional with the exception of only one. This is a trivial decomposition. So as we know the dimension of the factors, we can characterize when the action gives rise to a non-trivial or a trivial decomposition. So we have an equivalence between these 5 statements. The group algebra decomposition with respect to the quaternion group is trivial, is the same as to say that the dimension of the canonical subvariety fixed by Z is the center, is 0. And this is in turn equivalent to say that the dimension of AK is 0 for each subgroup, non-trivial subgroup of J. And there is another 2 other equivalents in terms of the numbers appearing in the way we read the rational of the analytic representation, and also in terms of the characteristic values of these matrices. Okay, and I have written in red this statement because this is particularly interesting for us because there is a similar definition in terms of Riemann surfaces, and this is the genus 0 actions. We said that a group G acting on a compact Riemann surface S is a genus 0, the action is a genus 0 action if the genus of each quotient, okay, maybe I need to write something like that, the genus of each quotient is 0. So of course, there is a clear, it's clear that there is an analog of situation in those cases. Okay, and what we know about genus 0 actions? But there is a topological classification of genus 0 action on Riemann surfaces, and it is very interesting because only a few groups agrees with this property. And one of them are the generalized quaternion groups. So let me fix the notation. Sigma B is this signature 0 and several B times 2 for 4 and 2 and minus 1. And we prove the following theorem. The action of the generalized quaternion group on a compact Riemann surface is a genus zero action if and only if the signature of the action is sigma b for some b non-negative b, of course. So there was an equivalence for each b, and moreover, for each b, we can construct a compact Riemann surfaces endowed with an action of the generalized quaternion group acting on it with the desired signature. And of course, well, the genus of the corresponding surface must be this yellow number. And we amend a small mistake because the previous result, the previous classification of these actions claim that B need to be odd. So we prove that there is no condition on B. So we amend this small mistake we found in an earlier work. Okay, another aspect we can consider are families of Jacobians or families of Riemann surfaces. And there is another link between another earlier work, Hidalgo and Quispe, studied in a previous work, Riemann surfaces with an action of this group. And they proved several results, but for the special case when m equals to the power n minus 2, we obtain the generalized quaternion group. So inside this set of groups, we found the generalized quaternion group. So in particular, their results for the generalized quaternion group, they said that there exists a unique compact Riemann surface with a triangle action of this group, and they give a complete characterization. The signature must be this signature, the genus of the corresponding surface is this number. They determined the full automorphism group of this Riemann surface, and moreover, they gave a class description as an algebraic curve. So they studied, so they restrict to the triangle case, in particular when the group is the generalized quaternion group. Okay, several information, many information about the triangle case, and the triangle case correspond to rigid points. So a triangle, a Riemann surface with a triangle action in the moduli space, it represents a point which cannot be deformed, keeping the automorphism. So they are rigid points. Of course, they are very interesting, but if we want to obtain moduli, meaning to moduli with the automorphism, we need to consider a more general or with families with dimension, and among them, the simplest one are the one-dimensional family or uniparametric families. So we pass from zero-dimensional case, the triangle case, to one-dimensional case, which is the one-dimensional families of surfaces. And let me recall this word. Family means a subset of the singular locus of the moduli space, all of them having an action of a fixed group K with a fixed signature sigma. We fix the group, we fix the signature, and consider all the Riemann surfaces with this action of this group with this fixed signature. And this is a family, and I'm going to avoid several details, but the family consists of several strata, which are in some sense the components of the family, and there is a way to compute, or at least to try to compute the number of components. And the dimension of the family, it can be written easily with this number. This is the dimension of the technical space of the corresponding signature. So in this language, triangle action are zero-dimensional families, and the next step is to study one-dimensional families. And this is our next result. We prove that there exist exactly n+1 complex one-dimensional families of Riemann surfaces with a group of automorphism G isomorphic to this number. There is exactly n+1, and we have a description of all of them. Here we have 1, we have 1, we we have 1, and here we have n minus 2. Of course, the genus change in all the cases, and the signature also change. So if we consider complex one-dimensional families with an action of the generalized quaternion group, we have only these possibilities, and we provide the signatures and the genus. Moreover, we were able to count in some cases the exact number of components. For example, the families, this family, and this family consists of only one stratum. So they are in some sense one piece in one sense. And in the other cases, we were not able to compute the exact number of components, but we were able to find an upper bound in these cases. And I want to mention that the problem of determining the exact number in general is difficult. Okay, another interesting problem is the problem of determining. All I have talked is about Riemann surfaces and Abelian variety with a group of automorphism G. But the Riemann surface or the Abelian variety can have more automorphism. So another general problem is to find the full group of automorphism in this case. And this is a challenging problem. It depends not, for example, in the case of Riemann surfaces, depends on the signature, but also on the geometry of the action. So it's very tricky. And but in the case of our families, we were able to describe in most or in all, with the exception of a finite number of exceptions, the full automorphism group of the members of the families. This is the idea. And I'm going to show only one case, the other are similar. For example, the members, all the members of the family F and 0, one of the families, have more automorphism than the generalized quaternion group. All the members have 2n automorphism, but they have 2n plus 1 at least. All the members have more automorphisms, and for all the members of the family, with the exception of finitely many possibilities, this is the full automorphism group. Most of the surfaces don't have more automorphism than 2n plus 1. Okay. Okay. Another aspect we can consider is that to relate again our families with genus 0 actions. And we have a characterization of genus 0 actions, and we have several families. So natural question is to decide which of our families admit have a genus 0 action. And only one of the families, one family, the associated action is a genus 0 action. And genus 0 action, in our case, is the same as saying that the group algebra decomposition is trivial. So for all our family, with the exception of one, the group algebra decomposition is non-trivial. So it decomposes really. And we can, of course, I have shown you that we have a very general isogeny decomposition, but in the case of these families, we can go further and to be more explicit. And I'm going to show you the result for only one family. The other ones are similar. For example, in the case of the family of the members of the family Fn2, the Jacobian decompose in this form. So in terms of one elliptic curve, twice another elliptic curve, this prime variety, and the product of several prime variety with multiplicity 2. Moreover, A1 and A2 are elliptic curves, but they have, as in the general case, geometric meanings, and they are isogynous to this Jacobian and this Jacobian respect. Sorry, I'm reading when I write this. I'm I'm trying to write the quotient of S by H. So for all the families, for all our families, we have this composition, beautiful decomposition as the yellow one. So, okay, another question we can ask is about the hyperelliptic situation. It's not difficult to show that among our families, only the members of this special family consist of surfaces that are hyperelliptic. And an advantage when we have hyperelliptic curves or hyperelliptic Riemann surfaces is that you can find in a very easy way an algebraic description in terms of a concrete and explicit algebraic curve. So the members, and we prove that the members of this family, remember, this is a one-dimensional family. They have a characterization as an algebraic curve in this way, when of course we need to have one complex parameter, and in this case the complex parameter is here. So as according we move the parameter t. T is a complex number, it cannot be 0 and 1. We move along the family, the one-dimensional family, and it's the explicitness of this algebraic description also allow us to describe, to give a realization of the quaternion, the generalized quaternion group action in terms of this mode. And the description is very, very explicit and very clear. Of course, we can do that only for this family because this is the unique case where their surfaces are hyperelliptic. Maybe the other case maybe are more complicated. Another interesting observation is that T is a complex number different from 0 and 1. In particular, we can take T equal -1. And if we replace T equal -1 in the green equation, in the yellow equation, sorry, we obtain this algebraic curve. And this is exactly the Riemann surface Xn1. Remember, the Riemann surface Xn1 is the unique compact Riemann surfaces admitting an action of the generalized quaternion group, a triangle action of the generalized quaternion group. So as a consequence, we have a very beautiful situation. We are in the moduli space, in the singular locus of the moduli space of Riemann surfaces of genus. I think the genus is n -1. And we have a one-dimensional family. Our family is Cn n-1. And one member of this family is this surface and X and 1. This is the picture in this case. So one of our family contains these special points, which was in some sense our motivation for us because we passed from the triangle case zero-dimensional families to the one-dimensional case uniparameter families. So it's very beautiful picture. Okay, and in order to finish, let me spend some words to consider the classical quaternion group of order 8. Most of the previous results are true for the case n equal 3, the case of order 8. Some of them are different because, as usual, the smallest case has a different behavior. So let me briefly review the case of the classical quaternion group of order 8. So in this case, the group algebra decomposition is the same as the isotypical decomposition, and it decomposes in terms of 5 factors: AG, 3 prime varieties, and another prime variety. And if, of course, the classical quaternion group has less representation, so the analytic representation always can be written in this way as a sum of these I'm keeping the same notation for the generalized quaternion group. In this case, we have 4 representation of degree 1, T1, T2, T3, and T4, and 1 representation of degree 2, theta 1. So if the analytic representation is written in this way, where A1, A2, and B are complex numbers, the dimension of these factors are very easy to compute. And very easy to compute. It's very direct and direct computation. And in the case of the one-dimensional families, we have only 3 complex one-dimensional families admitting the action of this one. And in terms of the previous decomposition, the previous notation, sorry, the family is the family F30, the family 32, and 2 families which are in general different. In the general case, in the case of the classical quaternion group, these families collapse. So we have 3 instead of 4 as the general theory. And for example, let me talk a little bit more about this family. This family consists of the Riemann surfaces with the quaternion group acting, the classical quaternion group acting with the signature 1, 2. Okay. Okay. As in the general case, this family consists of only 1 component, and we were able to prove that all the members of this family have more automorphisms. So if a Riemann surface belongs to the family F20, we are assuming that G of order 8 is inside out S, but all the members have more automorphisms. So they have 16. So all the members has at least 16 automorphism, and the structure of this automorphism group of order 16 is this one. And the signature of the action of this group is 2, 2, 2, 2, 2, 2, 4. And the last step is to ask if the surfaces have more automorphism than the 16, and the answer is no for all the members of the family with a finite number of possibly examples. Okay, and now the decomposition. The isotypical decomposition of the member of this family does not provide information, because this is the Jacobian of the quotient and the prime variety associated to this map, so there is no information. This is the group algebra decomposition with respect to the group G, the classical quaternion group. But I have said that all the members have more automorphism. So you can consider the group algebra decomposition with respect to the bigger group. And in this case, the Jacobian does decompose. So with 8 automorphism, we don't have an interest in the decomposition. When we consider the group algebra decomposition with respect to these 16 automorphisms, we can decompose the Jacobian. And it's very beautiful. The genus is 3, the genus of the surface. Okay, let me return of genus 3. So the Jacobian has dimension 3. This is 3-dimensional. So it can be decomposed, it's completely decomposable. It can be decomposed in terms of power of an elliptic curve times another elliptic curve, and both elliptic curves can be seen as a geometric, have a geometric meaning. The Jacobian of the quotient of A divided by A, and the Jacobian of the quotient divided by the group, the subgroup generated by A and B. Okay, and let me finish. I have 1 minute. Let me finish that with this interesting result. For each one of the families for each one of the complex one-dimensional families of surfaces with a classical quaternion group action, we construct a family of Abelian varieties which contain each one of the families of surfaces. So for example, in one case, we have a family of surfaces with Q8 action. We can construct a bigger, of course, family of abelian varieties which contain the original family. So we prove that there exists a complex one-dimensional family of principally polarized abelian variety of dimension 3 with an automorphism group. The members is the green group, satisfying the following property. Of course, Q8, this is the starting step, and the classical quaternion group acts on each one of these abelian variety, and we can write the representation, analytic representation, to characterize the actions. All the members decompose in terms of the product of an elliptic curve and an abelian surface. And as I have anticipated, the family of abelian variety contains the image, of course, the image of the family of curves. So we start with this family. We construct a family of abelian variety in such a way that one is contained after passing to the Jacobian, of course. And moreover, as the family of the abelian variety have dimension 3, we were able to describe it explicitly in terms of period matrices, and the family is described in terms of these matrices with there is one free complex parameter, only one complex parameter free. And this is the first case for one family, but we were able to construct similar families for each one of the 3 families with a classical quaternion group action. Thank you very much.
Thank you, Sebastian. Thank you. Thank you very much. And we have time for some questions or comments.
I have a question. Sebastian, thanks for such a nice talk. I was wondering if you looked at what happens with the automorphisms for singular stable curves. So if the automorphisms inside of a MG bar.
I don't know. This is a very interesting surfaces with nodes. You are
exactly. Yeah. Yes.
This is a very interesting problem. Indeed, this problem is very connected with the case of families, of course, because we have, for example, we have MG and we have MG decompactification, and then there are very interesting questions. For example, you can ask if we have a one-dimensional family trying to move to the boundary.
Exactly, yes.
And what happened with the automorphism? All the members of the family have the same group of automorphism, and what happened when we touch the boundary?
Exactly.
I don't know the answer,
yeah.
but I know that it's interesting.
Yeah, for example, in the example that you mentioned, the curve Cn(n-1) that you mentioned, right?
Yeah.
Which is parameterized, I think, by t different from 0 and 1.
Yeah.
So I was wondering if that curve, this is a rational curve inside of a MG or MG bar. So it probably is easy to see if that curve touches a boundary or what happens. And for example, if the point that the special point xn+1 that you mentioned, right? Is that point a singular point of this curve, or the curve is smooth at this point?
This is a very good question.
But it should be possible to see it, because it's fairly explicit, no?
Yes. Thank you very much for the question, because it's very interesting. I didn't think about that, but we can try it.
Okay. Thank you.
Are there more questions or more comments? So if not, let's thank Sebastian again. Thank you very much.